We now have a look at the recognition problem of beyond planar graph classes, in particular of one-planar graphs. So in the taxonomy, we are in this part here. And actually there are some differences between fixed rotation system and variable embedding. It could be that recognition is hard if we are given a rotation system, but not if we are allowed to choose the embedding, or it could be the other way around, or it could be that both are NP hard or both are polytime. For planar graphs, our first recognition algorithm was by Kuratowski's theorem. We showed that a graph is planar if and only if it has neither the K5 nor the K33 as a minor. Unfortunately, we cannot do the same for one-planar graphs. In fact, the class of one-planar graphs is not closed under edge contraction. That means it can be that we contract an edge, and what we get then is not one-planar anymore. To prove this, we will have a look at the n times n grid, and we will use another copy of it and connect them. This is the three-dimensional n times 2 grid. Obviously this is one-planar because here we have a one-planar drawing where only orange and blue edges cross. Now we want to do edge contractions here. For the blue vertices, we will contract every column into a single vertex. Now we only have one row of blue vertices and each of them is connected to n orange ones. And for the orange vertices, we will contract every row to a single vertex like this. And now every blue vertex is connected to every orange vertex. And we additionally have a path through the blue and the orange. So after these contractions, we got to the KNN. We have this bar here because there's an additional path, but a subgraph of this is the KNN. And already by edge density, it's clear that the KNN cannot be one-planar. And even stronger than that, Corsick and Mohr could show that for every n, there is an exponential number of distinct graphs that are not one-planar, but if we remove any edge, then it becomes one-planar. And this clearly does not hold for planar graphs. Well, that's another big difference. On the other hand, going the other way, we can always find a one-planar subdivision for every graph. And that's quite easy. Just after every crossing, we add a dummy vertex. Or between two crossings, we add a dummy vertex here. And now every edge is only crossed once, so we have a one-planar subdivision. So, we cannot use minors, and in fact, it's already NP-complete to test one-planarity. This be showed by Grigoriev and Bodlander, and by Corsick and Mohr. I will sketch to you the proof by Grigoriev and Bodlander. There they use a reduction from 3 partitions. So we have a bunch of numbers, and we want to split them into subsets of size 3, where every subset has the same sum. As a tool, they prove that this here is the only one-planar embedding of the K6. That means that we can force edges that cannot be crossed by replacing these fat edges by a K6. Now for the reduction, we use 2 of these wheels. Well, technically a wheel is only the interior part, but I will call this also wheel now. We have a bunch of fat edges that cannot be crossed, but we also have thin edges that can be crossed. Now, for every number in the input, we want to draw something through one of those bags, and depending on how large the number is, we want to use that many bags here. I will show you the example where we just have 6 numbers, so we want to split them into 2 groups of 3. If you have more, then you have larger wheels and you have more connections between them. So let's say this is our input, we have 1, 3, 2, 4, 1, 1. We can get 2 groups that sum up to 6. Now, for the number 1 here, we add 1 path between red and green. So here it has to go through some bag. Here it goes to someone, but no other number can use the same bag again because the gray edges can only be crossed once. For number 3, we do almost the same, except here we split it into 3 paths, so it has to use 3 bags here. And the number 2, it has to use 2 bags here. And we do the same on the bottom. We have the number 4 with 4 beds and 2 number 1s. So if we split this accordingly, then in each of these faces, we have to use 3 numbers, and the number has to be at most this. And since they always have the same number of pegs, we have to have exactly the number, which is the sum of all numbers divided by n over 3. And there are many more results. Even if we take a planar graph and add just a single edge, testing one planarity is already NP-complete. Even if we further restrict the graphs, so we require additional parameters to be bounded, for example, the bandwidth or path width or tree width, that basically tells you how close is it to a tree or to a path, then it's still NP-complete. And even if the graph is reconnected and the rotation system is fixed, we are not allowed to change it anymore, which we required to do here, because we don't know yet which path gets into which bag, it is still NP-complete. And actually most of those beyond planar graph classes are NP-complete to recognize. And we can also use this NP hardness of one-planar graphs to show it for other graph classes. I will show you here the proof for IC planarity. Here we have a one-planar drawing where every vertex can only be involved with one crossing edge. And to prove this, we used one-planarity testing. So we take as input some planar graph. We want to test if it's one-planar. Now at the beginning and end of all of those edges, we add this cycle of 3 vertices. We do this everywhere. Now, if we find an IC planar drawing for this graph, then after we remove this, we again get a one-planar drawing for the input. The only thing where we have to take care is, well, if one of those cycles gets crossed, then that's not something we really want to have in the one-planar, but we can't just take this edge and reroute it around this component to get rid of the crossings. And then the only crossings we have left are between the middle parts of the edges. You need a few more technical details, but basically that's the idea behind it. And we could also show that it's still NP-complete even if the rotation system is given. And if you look back at the overview, well, for fixed rotation system, it's hard for one planar, but polynomial time for maximum one planar. And for variable embedding, we can test it in polynomial time for outer one planar, outer fan planar, optimal one planar, 2-layer rack, or 2-layer fan planar, for example. Of course, those are not all graph classes. There are many more. For many of them, NP hardness or polynomial time is known, but for some, it's still open how hard it is to recognize.